like broken into three things. One is computing units, memory units, communication layer. Computing units, like basically CPU and GPU falls into computing units, and in a crude way, if you want to say, then it means that they are providing you ability to transform bit from one bit to another, right? Let's say you are adding two numbers on your computer. They had to be stored somewhere. They were represented as bits, and then they got calculated. Some fresh bits got generated, right? So manipulation of bits is possible via using computing units, and then there are processes running, and with each event, those processes state is changing. All that falls under computing units. We'll go into details in all three of it. Coming to memory units, basically memory units are used to store bits. Your hard drive, your RAM, your SSD, external hard drive, cache, all fall under memory units. Third thing is communication layer. How we take bits from one place to another, that falls into communication layer. And the question that we asked in communication layer is how fast we can move data from one place to another. Uh, Let me get into details of all these three components, and then we can go further. So, computing units, as far as computing units are concerned, as a programmer, what do you care about, right? So, one question that needs to ask is how many cycles per second. And what is a cycle? Basically, cycle is the basic unit of time used by CPU to execute an instruction. Every instruction goes through fetch, decode, execute, write back process, and one cycle is that basic unit in which the instruction time is represented. Okay, so think of it like heartbeat of a computer. So your clock speed is basically telling you how fast the heart of your computer beats. Okay, next thing is instruction per cycle. So how many instructions you can execute in one beat or one cycle, that is instruction per cycle. Now, why do we care about IPC? Because how many instruction you can execute in one cycle, that is the upper bound on how much parallelization you can achieve. Okay, and when we come to vectorization, this becomes an important number. Now these both things kind of we maintain a trade-off. Some people choose to have higher clock speed but suffer on IPC. Some have lower clock speed and they try to make it up on IPC. So if you want to check about your own system, right? So you can just type this command ls cpu, and it gives you all this information. Now, as far as CPU is concerned, we are interested in these three numbers basically. So MIPS is basically million instruction per second. So it is telling you that roughly it executes 6,587 million instructions per second. So that's what this number is telling you about. Now this BOGO MIPS stands for bogus MIPS. There is no way to tell exactly what this number is. It's just for reference. So you just open some other laptop and you look at the two numbers. Their absolute value doesn't is not accurate, but for comparison purpose, it is enough to tell you which computer is faster. This is basically your clock cycle, maximum and minimum, and it's in megahertz. Uh, Other than that, there are other things that LSCPU tells us, but regarding computing units, these are the main. Apart from that, it also tell you how much L1, L2, L3 cache you have, like 16 MB L3, 4 MB L2. So you can just type this command and see what is available to you. Okay, so coming back to this, so now we come to memory units. Memory units are basically used to store bits. Okay, and what are the measurements that we care about here? How much data a memory unit can hold, how fast it can read or write, and how fast it takes to locate data. So one feature of memory units is basically they are tiered. Tiered in the sense that there are different layers to it, and with each layer there are performance things, right? So fastest to access are CPU registers, but they are very few and very small in size. L1, L2, L3 cache are larger than register, but slower than that, right? So likewise, as we move upwards, we are getting into memory units which are like larger in size, but they are slower. Okay. Now you can't have everything in life. So basically, uh, you can't afford a 500 GB CPU registers, right? You can have a hard drive 500 GB or 1 TB, but CPU register or L2 cache, it's not likely, right? So having a tier structure is also beneficial when it comes to caching. We'll look at it in a while, but for now, uh, it's not legible, right? So legible, right? So here is a comparison of different tiers, how fast one is, right? And there's a scaled column which tells us how to compare, because it's hard to think in terms of nanoseconds, microseconds, right? So there's a scale version for us humans, and there is nanosecond version for machines, right? So one CPU cycle, if you consider it 1 second, then your L1 cache is already at 3 seconds. So I'll talk in scale terms. You can refer to the latency, for reference. By the time you move to across all the cache and you reach L3 cache, it's already 43 seconds. Now, in comparison to CPU cycle, your main memory access, your RAM access, basically it's already 6 minutes. Okay, your solid state disk SSD, which you consider to be faster, is like 2 to 6 days in comparison to CPU cycle. Uh, the old fashioned rotational disk that we used to have, they are already 1 to 12 months. Okay, internet access 4 years, 8 years, 19 years, based on which network you are accessing, right? And if you compare to this, your system reboots basically takes 32 millennia, right? If you think in terms of the system's heartbeat. So these are the numbers that you should have good idea about, and you should know that how your program is uh, interacting with these different memories, and what is the impact of that on the performance of the program. So this was about memory units. Now let's head back to communication layers. Basically, communication layers are how fast data moves from one place to another, and the questions that you need to answer or know answers for are how much data can a bus move in transfer, right? And second question is, that is bus width, and second question is, how many transfers bus can make in 1 second, that is bus frequency, right? If you compare it with the road, then bus width is basically how wide is the road, and how many transfers bus can make in 1 second, that is bus frequency. Now if road is wide, it can pass on a truck, but it's kacha road hai basically, right? Not that useful, right? Narrow road but very fast, again you'll have to do multiple passes to pass same amount of data. So these are the two numbers that you need to be aware of when it comes to data transfer. These things become very important when you use GPU also, right? So GPU is very fast in executing commands, but what is the bottleneck there is, how do you move data from CPU to GPU? So that becomes a bottleneck, and that's where communication layers come into picture. What are the different type of buses we have in the system? Basically, front side bus connects RAM to L1, L2 cache. uh, as we saw that RAM access is very slower in comparison to cache. So there is a specialized bus that move data back and forth from your main memory to L1, L2 cache. Then we have external bus, basically external devices, how they are connected to main memory and CPU. So for that we have external bus. And for peripheral devices like your pen drive, SSD, like external hard drive, we have PCI bus. So we went through computing units, memory units, and communication layer. Okay, so that is the rough abstraction of the computer you are using, and as a programmer you need to be aware of while you are writing programs. Now, this was about computer, and now the conversation is going into the realm of Python. So we'll be talking specifically in terms of Python. How can we write performant code in Python? Okay. So let's first talk about what are the drawbacks Python have, and then we can talk about how we can mend it. Okay. And why still Python is a good choice. So one is Python is a garbage collected language. Just like in C, you use malloc, alloc, like free. You yourself have to take care of the memory that your program is going to use. That is not the case in Python. Python do it on your behalf. You just have to declare variable, not even declare variable, just store something, and Python will take care of the memory that is going to be allotted to that particular variable. And after the life of that variable is complete, Python automatically frees it also. Now, what that does is it leads to memory fragmentation, because there are a lot of holes, because there is no fixed way in which memory is being allocated. Okay, and even freed when the variable life is over. Second thing is dynamic types and language not being compiled. Okay, so as you can see in C or Java, you have to actually declare your variables, what type they are, uh, right? And then based on that, memory allocation happens. Python doesn't have that. You can declare something in a variable, and then in the next statement you can just totally assign it to some other variable type, right? Int or string or anything. So in that way, Python is not static in nature; it's dynamic. And second thing is it's not a compiled language. So what is the drawback of a dynamic language in comparison to compiled language? It's that when you compile a program and your compiler goes through the program, it takes a lot of optimization decision uh, on your behalf without your knowledge also. But when your language is not, your program is not compiled, then all those optimization, the scope, there is no scope of optimization on compiler's part. Okay, and since Python is dynamic in nature, that scope is gone. Third thing is global interpreter lock. Well, it's yesterday's news because Python is soon going to remove global interpreter lock. But just for historical purpose, what is global interpreter lock? Uh, Global interpreter lock is the way in which Python handles race conditions. Okay, so Python interpreter, it at any point it gives its control to just one thread. Okay, now when only one thread has the control of the interpreter, then there is very unlikely for threads to compete and have race conditions. Okay, so that's what global interpreter lock did for Python. It simplified the solution to race conditions and deadlocks like anything, but it made multiprocessing and even multi-threading very much painful. Okay, so hopefully in the next coming versions this should be removed, but this is another drawback that Python had, still have. So if Python has so many drawbacks, then why still use Python, right? So basically it's batteries included language, whatever programmer needs, basic needs that are already built in without installing any new module, they are built in, right? Like packages like math, file IO, stream reading, all that. They are already present in Python, built-in features. Then it provides very good way to manage your environments. You are working on different projects, you can just have separate environment for different projects, and there are shells available. You can just spawn a shell and start entering statements over there. So that is there. It is faster to prototype ideas in Python. So before Python, what used to happen is for computing, we used to use C, Fortran, and all that, right? Now the science people who are like specialized in their field, when they needed to prototype some ideas, they had to learn those languages, and it provided huge uh, hurdle to them. So they were like separate specialists which were domain specific, and they were specialists who were like programming specialists. Python removed the need for this because it's just like a writing a pseudo code, right? So with less learning curve, more people came into programming and computing, which were domain experts, and with less resistance, they were able to try out different ideas. So that's the benefit of Python. Another benefit is basically Python allows you to plug in modules written in different language like C, Rust, Fortran, and you can just plug in into Python, right? That's how NumPy, Pandas, all these gain performance. They delegate the performance intensive part to Rust or C, right? So that's another benefit of using Python. Now let's discuss how can we profile our code and find out what are the bottlenecks over there. Okay, so let me move on to the notebook here, and screen. So let's talk about profiling. So simplest thing is basically you use time module, and just enter start and just enter end at the end of whatever statement you want to run, right? And just put an enter, right? And you'll get how much time this statement is taking. Okay, so that's one way, but you can't just add print statements, this time statement everywhere, right? And then later on comment. Sometimes you might forget it to comment it, and then that gets pushed to production, and then you are getting unnecessary logs in your files, right? So that thing is somewhat solved using decorators. So basically what decorator does is it's a piece of code that wraps the original function on which it is applied. So we have a lengthy function which sleeps for 4 seconds, right? And just by applying this decorator over here, what will happen is that it will act as if you are calling timer function. The timer function is calling lengthy function. So you get to execute this function, but it passes through some other flow. And what does our timer function does? It basically wraps the original function that it gets. Here are some time statement, and it returns how much time that is taking. Now what you need to do is, instead of commenting time statements, print statements, you just need to comment this. So when you run this lengthy function like this, right, it will print this, right, because it's wrapped and it is decorated by this decorator. Now you just comment this line.
But that's if you want to just time the lengthy function. If you would want to time parts of a function separately,
Yes,
that will still be a problem, right?
yes, definitely. That will be a problem. We'll come to it, how we can profile line to line. Okay. So basically, decorators makes it easier. Like you can create the timing code gets written just once and reused later with different functions, and you just have to comment these lines. If you are seeing that there are some functions which are problematic, you can just decorate them while development and then comment it out while pushing to production. So that's what decorator does, but they are not that huge what we can say improvement uh, when it comes to how much detail oriented we want to be in profiling our code. Okay, now second thing is basically there is a Linux command which is time, and you can run this and see how much time it's taking. So if I run this command, basically this is insertion sort, and I want to time it. This 10,000 means it will be run 10,000 times, and we'll get the average numbers. Okay, so real means here clock time. how much total time when we started running this and when it completed running, right? uh, User and sys. So basically user at program at any time run it's either in user mode or kernel mode. So user mode is basically 3.249 seconds here, and system mode is basically very negligible. So when does your program moves to kernel mode? Let's say that you want to allocate some memory, right? So memory or hardware, this is managed by your kernel. So you have to ask for to kernel. You have to switch from user space to kernel space to get that thing done. So basically, these two numbers are user space and kernel space, and this is the total of that. So again, this is like this works on a script as a whole, but not at a function level like time function does. But still, it comes handy. Just a quick command type on your terminal, and you get to see the numbers.
So
Now,
so user so user is describing the time the program has taken while in user mode,
yes,
and similarly for the system.
for the kernel, it is defined by system. Okay, so so far so good, but they are not that powerful. And now let's move on to something interesting. Line profiler. Basically, what line profiler does is line by line, it tells you how much time each line is taking in your program. Okay, so what I'll do is I'll show you. This is the insertion sort program that we have run, right? And in order to for line profile to know which function to profile, it has to be decorated with @profile. Okay, and now when I run this, so basically I get some output like this. Okay, so what I'm doing is basically I'm line by line analyzing what how much time this script is taking. Okay, so I'm running the script, but I'm profiling a particular part of the code which I have decorated with @profile. Okay, so what are the different information we get to know from line profiler? How many times that statement got executed? Okay, this is told by hits. How much time program spent executing those commands or that particular line, that is told to us by time. Per hit, basically just the average, like divide by this, we get this. This is what is interesting to us. What percentage of total time the program is spending on this particular line? Now, in insertion sort, basically, it is very much apparent that there is a loop inside a loop. So what statements are getting going to be executed most number of times, right? Which is clear by here that our program is spending 32% of its time executing this line. Okay, so here it is like loop inside loop, very much apparent what is running more, right? But when you write complex code bases and all that, it becomes very tedious to debug where your program is spending so much time. And in that case, these line profilers come very handy. So I'll repeat how do we. Yeah, Tarang, please carry on.
Sorry to interrupt, but here for the for loop line, the for loop will execute n number of times, right? Many number of times. So the percentage time of 0.6, does it indicate the time the system takes for running one iteration, or the n iterations?
Okay, so basically, percentage time tells you that overall how much time was spent running this statement. Now we might come back to it again and again due to loop. Okay, but time will tell you how much total time it spent.
Total time.
So it's not one time how much it spent,
Okay.
it's total time. what you are talking, that this statement, how much time roughly it takes while executing once, that number is dedicated, you know, over here.
Okay. Thank you. Thank you so much.
Okay, so basically, how do we use it? Whatever program we want to profile, let's say we want to profile this function line by line. So we add a profile decorator over here. This is the part of the like code we have written. If we want to run it not via kernel like line profiler, but directly, then this profile won't be available. Just to handle that exception, this code is added, and now by doing this, this script will run as expected. If you run it via Python, then it will be running as it is. If you run it via line profiler, then it will give you line by line analysis of your program. So that's about line profiler. Now next is basically a more detailed one, which is perf module. Okay, perf module gives more detailed information about the behavior of your program. So let me run this and we can discuss. So now when we do performance analysis of this particular function, right, then it tells us very detailed information about the program. So basically cycles tells us that how many CPU cycles this program stayed for or ran, right? So this is that number. Another thing is how many CPU instructions your program gave to system. So this is that number. Cache references is how many times total your program referred to cache. Okay. Uh, Cache misses is something that how many times data was not found in cache and yet had to be fetched from main memory. Likewise, there are branches and branch misses. So let's say that your program is like line by line executing one statement by after another. So what interpreter does is it prefetch or predicts that okay, this is the next statement to be executed. So it predicts it, right? Now whenever there is a if else kind of loop, it still predicts it, but based on the if condition, it may fail in prediction, right? So branches tells us how many such if else kind of situations are in the program, how many times it was faced, and branch misses basically tells you how many times it predicted wrong the branching of the code. Okay, then we have faults. Basically faults is like how many times you had to ask for memory and have to go to kernel mode, right? So that is basically faults. So that's how perf module gives us very detailed instructions. Let's say you are working with vectors and you are like looking forward to leverage caching and all that, right? So this definitely helps. Uh, these two numbers will tell you whether what you intend to do are actually happening or not happening. Okay. So these are some handy tools. There are more. This list is not exhaustive, but they are helpful to me personally. Whatever I need, I usually get. This is very much helpful when you are reading some new code and you are trying it out and just trying to debug why it's slow. Uh, Running these tools, running code profiling helps you narrow down that bottleneck very quickly. Otherwise, it takes manual inspection and figuring out uh, where it is troublesome. So there are some to-dos when you are profiling code to be reported to upper management or your teammates. Then there are some best practices to it. So disable turbo boost in BIOS. That's one thing. Uh, Disable operating system's ability to override the speed step. This is also a setting. So I haven't gone into a detail of it, but definitely you can check it out. You only use mains power, never battery power while profiling, because what happens is that your computer or your laptop takes measure to preserve battery and dumb down kind of the machines, right, in order to do so. So whenever you are doing profiling, just ensure you have enough battery and it's on mains power. A lot of times there are like background processes running and that they interrupt in your profiling, so it's better to check uh, what are running and you can just disable them. Okay. uh, Let me just switch to slides. It's visible, right? More clearly. Yeah. Run the experiment many times, then take average. It's a good practice. Then several times, what happens is your CPU does context switching a lot, and that affects your numbers. So basically, you can drop to level one, so that whenever you are doing profiling, that program gets the preference and that stays on the, just to avoid context switch and your program getting switched out. You can also reboot and rerun the experiment just to confirm the results of profiling that you are getting. So that was about profiling. Now we'll get to see some interesting things, you know, behaviors that some data structures in Python show. And so let's get to it. Let's talk about list. Basically, list का property होता है कि that they are dynamic in nature, and because they are dynamic in nature, you can store anything and everything in a list. Okay, you can just store a number, a string, another object, another list in same list, right? So in that way, list is dynamic in nature, and it is very much convenient for user, but it doesn't come for free. Okay. uh, there are certain things which happens under the hood, affects the performance of the list, which user may not be aware of. Okay. So let's talk about this. Like, one thing is resizing. So one thing is, when you create a list, some memory is allocated to it, and then when you start adding items to it, the memory that you got from the kernel got finished. And that time what happens is, you have to again go to kernel mode, take a bigger list for future editions, come back, copy the existing list into that list new, right? And then start additions more, right? So resizing in background makes appending to array slower, because it gets exhausted, again memory allocation. Not only is it slow, but it's take more memory than required usually. Because what happens is, when your memory existing memory got exhausted and you are bringing another memory asking, right, you always over allocate it, because you don't want to fall into that same situation soon. So you'll always take more provision uh, in a list while appending it, right? So the side effect of that is that you are storing 10 numbers, but it will take space for a lot more numbers, and that is not quite apparent that why it is taking, right? So we can just quickly run some programs and see that in action. Okay, so I'll switch to notebook, and let's see that in action. So this is basically list comprehension on 10,000 numbers. Okay, now when I run it, it takes 267 milliseconds. Okay, now this is basically, I'm initializing an array and then appending it one by one 10,000 times. Okay, and when I run it, it takes roughly not double actually, but lot more time than the previous one. And we can guess why that is happening. Because you are appending to that list one by one, it is again and again getting exhausted, resizing in done, copying, uh, switching into kernel mode is happening. That's why it is taking more time. Now let's look at how much memory does this take, right? So when you use memit on a cell, basically what it tells you is what is the peak memory and what is the increment. We care about increment. Increment tell us what is the impact your memory had, like your program or your statement had on the main memory. So when I run the list comprehension thing, the increment I see is basically 0 MB. Okay, and when I run this is the increment I see. And why is that happening? Because of the over allocation of memory that we are doing when we are actually adjusting, right? So let's say that when the 10,000 numbers are already there, the state of list is that it's a lot of it is already empty. And because of that over allocation, this is the memory footprint appending to array is having in comparison to let's say just adding a like using list comprehension instead of appending it one by one. The advantage of list comprehension is basically uh, you're doing it at one go, so only one memory allocation is happening, and you are kind of bringing in only that much as it is required, or slightly more than that, but never as much over allocation as it is happening in this thing, appending elements, right? So just to wrap it up, basically memory allocations are costly. You know, you have to switch, like whenever you assign a value to variable interpreter, like the interpreter needs to talk to OS. The more it has to does that, allocate new space, ask for it, get it approved, it is time consuming when it's compared to normal statements that you CPU instructions that you run in your program. uh,
Is there a reason why peak memory is different, like, or it is expected to be somewhat different in every run?
so basically peak memory, what it does is like is the highest memory footprint that was while running your program.
Right.
So it's not only depending on this, but it's also dependent on the other process
Right.
that are. So it's just the we are interested in the relative part, how much this statement change the memory footprint.
Right.
So this is what we care about, and this is also dependent on the extrinsic factors. So I think my battery is expiring. Let me switch to power. Oh, no. Yeah. So coming back to list. So key findings are one is memory allocation, which are expensive, time consuming, and when we do it again and again, they are like pain. Another thing is memory fragmentation. So lists are dynamic in nature. Because of that, what it happens is you can fit anything and everything into a list. So because of that, they are not saved in a contiguous memory location. You are saving those items that are there in the list at different places, and then you are storing the reference to those places in the list, okay, for the user. Now what that when that happens, all your items on the list are scattered at different memory locations, right? So there is no vectorization possible, because to operate on a list you'll have to like refer to those different memory locations. So not much vectorization possible. And since they are not stored in contiguous memory locations, there will be a lot of cache miss, because cache is based on temporal locality and spatial locality. There is no spatial locality here since items are scattered, right? So that will lead to cache misses. So let's quickly
So currently, let's move on to what is list comprehension.
okay, so basically, list comprehension is a way in which you can create another list based on some list. Okay, so let's say you have a list, right? This, right? Now you can create as many lists out of this original list just by applying something on the elements of this. So if I do I into 2 for I in A, this is list comprehension. I'm taking an existing list and then applying some function on each element, and then I get another list which is function of the previous
What is
list. So,
what is big memory and increment?
yeah. So when we did memit on a cell, basically we got two numbers. One is peak memory, another is increment. Now peak memory is basically we are taking a look at how much memory is currently occupied. Okay, and you will be concerned about that number only when you are doing a very RAM intensive job and peak memory is reaching the overall capacity, right? Then only you will care about. But when you are actually profiling a particular function or a statement, then you need to care about the increment, because that is a relative difference your statement caused on the overall memory footprint.
But why is this important?
It's important because you are calculating, you are interested in how much memory your program is taking. You don't want your program to leave lot of memory footprint. So that's why you need to keep an eye on the increment. Okay. Uh, yeah. So moving on to now that we have understood the drawbacks of list, it's good time that we compare it with NumPy arrays. They look very same, but NumPy arrays provide some very good advantages which lists are not able to provide. Uh, we create different functions over here. Okay, uh, some are using NumPy arrays and some are just using list of numbers and looping over it. Okay, so as you can say that when we want to calculate the magnitude of a vector, then we take a dot product with itself. Okay, uh, in terms of list, what we do is basically we multiply each element by itself and then add it. Okay, that becomes our norm of that particular vector. So we have four functions. Basically here what we are doing is uh, we are looping in the vector one by one. Okay, adding it, like multiplying it with itself, each element, and then adding it to norm. Okay, then in the second case what we are doing is we are using list comprehension instead of looping and then summing it over. Then third thing is we are actually taking a NumPy array as input, we are multiplying it with itself, okay, and we are taking sum. And the third part is there is a built-in function np dot dot that calculates the dot product of one vector with other. So what are our findings over here? So for the sake of time, I won't run it but I can show you results from the previous findings. Okay, so when you do these are I think thousand numbers as a list, and when you are doing calling the normal square list function, it is taking 42.5 milliseconds to run that function. Now when you are using list comprehension, it's kind of taking more time, but the moment when you move to NumPy arrays, it is taking in milliseconds rather than, so order of magnitude change when you switch from Python list to NumPy arrays. So why does NumPy arrays perform better? So basically, before that, let me compare why these two are performing, right? So NumPy dot function uses a specialized function, np dot, right? And this one basically it uses NumPy arrays, but it is explicitly doing the sum and product part. Okay. Now specialized functions are optimized in such a way that they are better performing. So that's why we see some improvement in dot directly, right? In comparison to the one where we did the explicit product and addition. So why are NumPy arrays faster than lists? There are two reasons. One is that NumPy code is specialized code. It is written in C. I think there is a C blast library, right, for linear algebra. Uh, it's written in C and then being used in Python. So Python delegates performance sensitive tasks to these C, Fortran, Rust modules, but those changes are transparent to users. Okay, so that is one thing. It's specialized code. The second thing is that unlike list, which is dynamic in nature, non-contiguous, NumPy arrays are actually contiguous. So they are like stored in the memory one by one. So when they are stored one by one, they are in better situation to benefit from caching. That's one thing. And second is they are also open to vectorization. So what is vectorization? Vectorization functions using this concept called SIMD, single instruction, multiple data. So when you have different data spread in a vector or in a matrix, and then you do a dot product with some other vector, what you are doing is you are giving multiple data and asking it to perform same instruction. So that is like parallelized like anything. You're not looping over them one by one. You are doing all that instructions in parallel. So that way NumPy arrays are faster than Python lists. So that was about list. Now let's
When NumPy arrays store general objects like another list or strings, etc.
not quite. No, they have to be of same data type, and if they are not, then they are made forced to have same data type. Let's say a string or okay. So that was about list and NumPy arrays. Now let's look at something called dictionaries and namespaces. So when we run a Python statement and we call something, a function or a variable, then there is a series of lookups that happens. Okay, first that variable is looked up in the local space, then it is looked up in the global space, and then it is looked up in the built-in space. Okay, now let's look at these three examples and it will become more clear to us. uh, all these three functions basically does the same thing, but their inner working is different. Okay, so let's say that we want to take some value x and we want to calculate the sign of that particular x. Okay, so now here what is happening is we have already imported math, right? And this function is doing math dot sign x. Okay, now what is happening over here is math is being looked up in global dictionary, right? So that's one dictionary lookup. Sign is being looked up in math ka local math module mein, right? So that's another lookup, and then there is a local lookup for x. So there are three lookups happening over here. When we are doing this from math import sign, then what is happening is sign is being looked up in globals we found there, right? And x is being looked up in locals. So they are like uh, one dictionary access in globals and one local access. Now what if we do this, right? Sign is equal to math dot sign. Now there are two local axes. Okay. Now this example is not to encourage this kind of thing like you do, but just for the example, the different number of accesses, dictionary accesses that you do, in namespaces, they are taking this. Now, when we compare the timings of these things, right, it has become very much evident that less number of lookups is leading to less number of time. Uh, the first thing, it's two dictionary lookups, one local lookup. It is taking 60 nanoseconds, right? 60.9 something. One dictionary lookup, one local lookup, 60.5. And then when we are using two local lookups, even less time, right? So there is no performance lesson over here. Just to understand that there is a data structure dictionary which is ubiquitously used in Python everywhere, right? And just how much impact dictionary access can have. To blind eye, it can be like instant, but when we time it, we get to know that okay, it has some cost associated with it. So this is like when we timed it, we can actually verify it, how it happens, right? So the first function, we did load global, load method, load fast. Load fast is basically our local access. Load global and load method, they are our dictionary accesses. In test 2, we have one global access, one local access, right? As it is apparent from here. And here we can see that there are like two local accesses, sign and x, both are found in local context. So we got two local accesses. This is basically, it breaks down the bytecode and give you step by step what is happening, right? So our functions are like just one statement, but it is further broken down to all this, uh, and Python interpreter is making it happen. So
Sir, you told that dictionaries are ubiquitous in Python. Can you please elaborate this?
okay, so ubiquitous means they are like everywhere. Uh, how do you explain? Let's say we have a class. Okay, we define a class, we create an object out of it, right? Now all the classes, the properties of the classes, right, of the object, even though which we are not explicitly setting, they are also being stored as dictionary. And when Python interpreter need to access different properties of the classes, it implicitly calls and do dictionary lookups. So likewise, the interpreter relies heavily on dictionaries. It uses dictionary as a data structure for its inner working also. So it's available to user also who is programming. It's also what the interpreter is using to do its bookkeeping.
This is in the same way that in some slides back, there was a slide where we define three functions and we are looking up math function and stat function and so on. So that looking up was done by dictionary.
Uh, Looking up was done by interpreter, but the storing of that was done in dictionary. So they were relying on dictionary, and there were dictionary lookups happening to run this particular function.
And so you mentioned that stan function will be looked up in the math module. How this was a division by the interpreter.
Yes. So when we say math.sinx, right? So the sign, we are explicitly telling the interpreter that you will find sign in math.
Okay.
So
Yeah, telling. So from that the information the Python could uh, know.
yes. So basically, when we object dot something, right? So we are saying to Python interpreter, you don't need to look it anywhere, right? You will find it in this object. So that's what is happening over here.
Got it.
Okay. So this was about dictionaries. Uh, Now, where from here? Like one thing that you can try out is how you can write programs in language different than Python. Let's say C, Fortran. 5 minutes. So you can write programs like small programs in C, Fortran, Rest, and then try to integrate in Python. You can also explore the NumPy Pandas code and see how they are doing it. Even as far as NLP is concerned, you can even look at the spacey code base, and you can see that a lot of heavy lifting being done by these non-Python modules. Another thing is multiprocessing. How do you use all the cores of your machine by using multiprocessing? That can be explored. Uh, you can also look at distributed processing. When can you run a program and distribute it to several clusters on the same machine, or use more machines? And then you can also explore how you can make your programs use less RAM. So one of them is using iterators, using generators. You can avoid loading all the data into a machine at once. So that's also one of the ways, but there are many. And yeah, this is something that brings us to the end of discussion. There are references attached, so I'll be sharing the notebook with you soon. And if you go through the references, then it will take you to more places, a lot more interesting places than what we discussed in this talk. This book is very handy. High Performance Python. It talks about different aspects of Python, and majority of the content is like inspired by the book only. And then there are some other links. So yeah, any questions?
Can you go back to the comparison between when you were timing that while loop?
Insertion sort example, right?
Right.
Okay. Let me run it over here.
So that while part is taking so long probably just because of the comparison, right? Because there are two operations like the
Not exactly. While part is taking longer than the rest of that, because the statement is going to be executed more than or equal to the statement below it. Because there will be some conditions where this will be failing, and the statement will be being executed less.
right.
So,
So that difference is small. That's fine. I'm just trying to understand the difference between for and while.
okay. For and while. Okay. That numbers should give us the answer, right? So this loop is basically, this statement is being executed by 99 numbers of time,
Oh,
because we have like 100 numbers to sort, right? But this statement is getting executed inside for loop, right? And again and again. Once these are getting executed, it is again coming back to this, again coming back to this, right? So these numbers, because of sheer numbers, this difference is coming. Otherwise, this comparison and all, it's not that significant introduction in time. It's just because the frequency is more.
right. But it's still like even if you normalize it by the hits, number of hits, it's roughly 100 versus 5,000, so 50 times more.
What numbers you are comparing?
Row 16 and row 21, 22.
Row number 16 and 22. So basically,
100 versus 5,000, so 50 times.
yes.
And 50 times 0.4 would still be 20, so it's still half.
We can attribute it to, so there is an array access, memory access
Right.
to some other memory location, right? And here what is
Right,
happening is,
that's probably the
here just happening is just incrementing, and
right. So it's probably not because of the comparison, it's because of that array of J access.
yes, allocation, yes. Here also you have to access a particular element of an array.
Right.
So you have to go to that location, right? So perhaps that is what is bringing in the significant time difference. So that brings us to the end of this event. I would like to thank everyone who took time to on who took time basically on weekend to attend this talk. I'm sure you found it helpful.